Hey friends, welcome back. So this time we've got a problem where we're given two of these limits. So specifically we have a function f of x, which we don't have much information about, but we do happen to know that the limit of f of x as x approaches 2 is the number 7. And similarly, we don't have much information about g of x, but we happen to know one value of a limit. Okay? And we would like to use that information to find the value of this limit. So when I ask my students this question, almost every time I get the response, well, can't we just plug in 7 for this and 1/2 for this and do the following? As in, here we have 7 subtract 16 times this value 1/2, which is 7 subtract 8. So we get the answer -1. And this is completely valid. This is the way to do it, and this is the answer. But what I want to talk about today is a little bit more about why we're able to do that. And I'm not going to go into the proofs, right? Unfortunately, at this stage in calculus, there are a lot of these trust me bro moments where I say, okay, this is a thing that you're allowed to do. I'm not going to prove that you're allowed to do it, but I'm going to reference some property that has been proven. And maybe someday when I'm less lazy or stupid, I'll actually put together a video where I do go through the detailed proofs of those things, okay? But this thing that we just did, okay, I want to clear the air. Did I assert that f of x equals 7? Right? And this is sort of like a weird thing, saying that, am I saying that f of x, the function, which could have many different outputs for different values of x, always outputs the number 7? As in it's a constant function? No, clearly I'm not saying that. Am I saying there is some value x equals c such that f of c equals 7? Am I saying that? As in, like, I can replace somehow this function f of x with the number 7 because at a specific value of x, I get the number 7? That's not even what I'm doing either, right? And even if I took the c and said it's the number 2, right? So I'm saying specifically f of 2 equals 7. I'm not saying that anywhere, okay? What I am saying is that I can take this and somehow break it down, right? Specifically to say that the limit of f of x minus 16g of x as x approaches 2 can be broken down as the limit of f of x as x approaches 2 minus 16 times the limit of g of x as x approaches 2. Okay, and I guess I can put, bigger parentheses around these things to indicate where I'm really breaking it down, right there. Okay? So if I can go from here to this second line, which it turns out I can, then I can take this and replace this limit with the value 7, because that is exactly the given information, right? So this gets replaced with 7, and then this gets replaced with 1/2. So that's what I'm doing, and I want to make it very clear that at no point am I trying to actually replace f of x with the number 7. I'm specifically replacing the limit of f of x as x approaches 2 with the given value 7. And showing your work like this is honestly what indicates to your instructor that you know what you're doing, and on more complicated problems, this is sort of how you get full credit, where otherwise you might get docked points. All right, so here I've written out 4 important properties of limits that we're going to end up using a lot, whether or not we sort of explicitly reference them while we're using them. Okay. So I want to state, to make this very clear, that these are all provable using the formal epsilon and delta definition of a finite limit that I alluded to when I first started talking about limits, but I'm not going to present those proofs to you today. So I'm going to add these to the sort of pile of trust me bros, which we may or may not resolve at some point in the future. But let's talk about how these apply to the example we just did. So if this limit exists and k is a constant, then we're able to say the limit of this constant multiplied by the function is the same thing as taking the limit of the function without the constant and then multiplying by the constant after the fact. So we just did this in the previous problem by saying, oh, the limit as x approaches 2 of negative 16 g of x is the same thing as negative 16 times the limit of g of x as x approaches 2, right? Because we were given this value, and we could simply multiply that by negative 16. If we have two of these limits existing, one for each function, then we're able to say the limit of the sum is equal to the sum of the limits. Okay. So this g of x right here, so I'm going to go ahead and, I guess, replace this with the letter h and write something like this. I'm going to say the limit as x approaches 2 of f of x plus h of x, and then I'm going to go ahead and let h of x be the same thing as negative 16 g of x. Okay? Then I can say, hey, do each of these have a limit as x approaches 2? As in, are my conditions true? Well, in that problem, I knew the limit of f of x as x approached 2. And to ask, does the limit of h of x as x approaches 2 exist? I can remind myself that, oh, well, I already did that up here. I was able to say if this exists, then I have a value for that thing. So that means the limit of h of x as x approaches 2 does exist. Okay, I'm getting a little bit into the weeds, not too much. Don't worry too much about the individual words I'm saying, okay? Just general ideas. So I'm able to break this up into the sum of limits. So I'm able to say, oh, this is the limit of f of x as x approaches 2 plus, right, the limit here of h of x, which I can even just rewrite at this stage as negative 16 g of x. And I can use the first property to resolve this part and then add those two results at the end. Okay, and we have these other two properties that we didn't use in the previous example, but we'll just talk about them real quick. If both of these limits exist, then it turns out the limit of the product is equal to the product of the limits. And then if these two limits exist, I can do a quotient, but keeping in mind that since I'm going to divide by something, at this stage I need to make sure that the divisor, the denominator, is not actually equal to 0. But if it's not equal to 0, then I can do this. So before we move on, I've heard, right, people say, looking at this list, well, duh, why wouldn't any of these be true? Like, I mean, sure, you're just multiplying a number. Sure, you're just adding things. You're just multiplying things. These properties should be true. And I get that. Intuitively, I think we'd run into some problems if we couldn't establish these properties. But I think it's fortunate for us that we have a system of math that supports these intuitive ideas for limits, just like we would have with values of functions. And I want to stress the importance of these kinds of properties. Like, I like to think of these as building blocks, because when we have properties like these in a system of math, that means all we have to do is establish very basic ideas. And then we can use those basic ideas together to make more complicated ideas, and take those, put them together to make more complicated ideas. So these really allow us to build very complicated things out of simple things that we can prove very quickly. So I want to emphasize the sort of value of these. Maybe some quick examples before we go. So we've got 3 given limits. They all exist because we have values for them. And we would like to find the limit of this quotient that has a product in the denominator. Okay. So the logic is, in order for us to proceed, we need to make sure that the limit of the numerator exists. Okay, it does. And the limit of the denominator exists and is not 0, because we don't want to divide by 0. So to get the limit of the denominator, I guess first we want to go over here and say, consider the limit as x approaches -5 of g of x times h of x. Now, if we know that the individual limits, both of g of x and of h of x, as x approaches -5, if they both exist, which we know they both exist, we can apply the property that says the limit of the product is equal to the product of the limits. We have both of those values. That's -4, that's 1/2. That's -4 times 1/2, which gets us -2. Okay, so we understand that this exists and it is not equal to 0, which means we can go over here and say, all right, this is the same thing as taking the limit of the numerator and dividing it by the limit of the denominator. We have a value for that. That is 3. And we have a value for this right here. We found it was -2. So we can say 3 divided by -2 is -3/2. And there we have our answer. We've got two graphs, one for f of x, one for g of x. Our goal is to find the limit of the sum of the two functions as x approaches 6. Now, we could certainly construct the function f of x plus g of x by taking all the y values here, adding them to all the y values here, like with a chart or something, and once we have that function, we could try to find the limit of that function. Certainly a viable technique, but we're not going to do exactly that here because we want to big brain it using the properties of limits. Okay. All right, so first things first, let's bring back this list of properties, okay, and we're thinking about adding. So we're asking ourselves, can we apply this property? Well, in order to do this, we need the limit of f of x as x approaches, in this case, 6, to exist, which it doesn't. How come? Because the left one-sided limit, which is going to come out to be 9, and the right one-sided limit, which is going to come out to be 12, are not the same value. Okay, so if they don't match, you're not approaching the same y value from both sides, you would say the limit does not exist. Okay, and we encounter the same issue over here because the left one-sided limit and the right one-sided limit do not match. And notice it doesn't matter that there's a closed circle, or open circle, open circle. That doesn't matter when we're discussing what we're approaching. Okay? So going back to here, we have violated these conditions, which means we cannot use this property, right? Because neither of these things is a number. Well, you can't add two things that are not numbers. Well, does that mean this limit does not exist? Turns out the limit does exist. And we got to be able to figure out why and how to find it. Okay, so to break it down, I could say this exists if I can think about the following. What if I take the left one-sided limit? Now, if I can apply the left one-sided limit to each function individually and have that left one-sided limit exist, then I can actually apply this property for just the left-sided limit. So here would be x approaches c with a little minus and a little minus on all these things, and I get to do that. Turns out this property applies to a one-sided limit as well. Once again, a trust me bro moment. Okay, so I'm going to do this. Here and here. So this exists because I can take a left one-sided limit. It looks like I'm approaching a y value of 9. So this is going to be 9. This also exists. Based on the graph, from the left, my y values are approaching 5. All right, so this value 14 is the left one-sided limit of this sum of functions. If I do the same thing for the right one-sided limit, sure. If I can establish that the individual limits exist, then I can use the sum property. And looking at the graphs, I can verify this exists. Approaching from the right, my y values are approaching the number 12. This is 12. Plus, over here, as I approach from the right, my y values are approaching 2. So I get 14. Now here's the deal. My left one-sided limit and my right one-sided limit match. Doesn't that mean that the limit as x approaches 6, right, from both directions has to be that number? Yes, it does. So I would conclude, therefore, the limit as x approaches 6, f of x plus g of x is equal to the number 14. Definitely some cool problems using the properties of limits. And always remember that when you have a limit as x approaches some number, x is approaching that number from both sides. So sometimes you have to consider the one-sided limits from the left and from the right separately in order to establish the overall limit from both sides. All right? Hopefully you learned something. Hopefully that was fun. See you guys next time. Peace.